Let's dive right into this explainer and unpack the incredibly dramatic origin story of the largest planet in our cosmic neighborhood. When we look up at the night sky, it's so easy to just imagine the planets as these static, peaceful spheres that have basically always been exactly where they are right now. But the truth about our solar system's history, it is far, far more chaotic than that. And Jupiter happens to sit right at the absolute center of all that chaos. So today, we're going to dig into the violent formation, the wild migration, and the deep, dark secrets of the King of Planets.
We're all pretty familiar with that majestic, iconic beauty, right? Those gorgeous, swirling bands of orange, white, and gray. But there is a massive amount of incredibly turbulent history hiding just behind those clouds. That seemingly calm exterior we see from millions of miles away actually masks a world of staggering pressure, bizarre chemistry, and a past that literally reshaped everything around it.
To really get to the bottom of this mystery, we have to completely reframe how we think about this massive world. A lot of times, we casually call it a gas giant, and we kind of picture it as this passive, quiet observer just chilling out in the outer solar system. But the data tells us a completely different story. Because of Jupiter's absolute mammoth size, it holds 2.5 times the mass of all the other planets combined, its gravity has been this dominating, bullying force since the very dawn of our solar system. It didn't just quietly form, it actively engineered the planetary neighborhood we all live in today.
Now, there's this super common myth you'll hear all the time, that Jupiter is just a failed star. People love to argue that if it had just gathered a little bit more mass, it would have ignited nuclear fusion, and we'd be living in a double-star system. But the number 75 is absolutely crucial here. To actually spark nuclear fusion in its core and become a true star, Jupiter wouldn't just need a little more mass. It would literally need to be 75 times heavier than it is right now. So honestly, calling it a failed star just doesn't do justice to what it actually is, a wildly successful planetary giant.
What's truly mind-blowing is what it's made of. Instead of looking at it as a failed star, we really need to view it as a massive cosmic time capsule. By mass, it is essentially 75% hydrogen and 25% helium. And this is a huge deal because it perfectly matches the chemical makeup of our Sun. Because it was so incredibly massive, Jupiter was able to hold on to its original composition, basically capturing a pristine sample of the exact primordial solar nebula. That original cloud of gas and dust that birthed our entire solar system.
And because it held on to all that primordial stuff, calling it a gas giant is actually a bit misleading. Thanks to its immense gravity, the atmospheric pressure deep down inside is just unimaginably high. It's so intense that it compresses the hydrogen gas not just into a regular liquid, but into this bizarre electrically conducting fluid called liquid metallic hydrogen. And all of this surrounds a super dense, partially dissolved core of rock and ice. Since the vast majority of the planet is made of this compressed liquefied hydrogen, a lot of scientists point out that we really should be calling it a liquid planet.
The whole why this matters really comes down to this idea from Scott Bolton, the principal investigator for NASA's Juno mission. He calls Jupiter the Rosetta Stone of our solar system, because it acts like this perfect chemical time capsule. Deciphering its origin and how it evolved translates directly to understanding the formation of our entire solar system. So unlocking Jupiter's secrets is literally how we figure out how the Earth came to be, and how our own little world eventually became a haven for life.
But getting those answers is definitely not easy. For centuries, this massive maze of violent storms, like the famous Great Red Spot, and incredibly thick clouds have totally blocked us from seeing what's really going on inside. And if you try to just drop something in, like the Galileo probe back in 1995, it just gets completely crushed beneath the pressure of the clouds. It is definitely not a welcoming environment. So to peel back those opaque layers, scientists have had to rely on really clever indirect measurements and unbelievably advanced computer modeling.
And to finally peer beneath those clouds without getting crushed, an amazing recent study from researchers at the University of Chicago and the Jet Propulsion Laboratory built a totally revolutionary model. This isn't just looking at the chemicals in isolation. It actually links atmospheric chemistry directly with hydrodynamics, basically the actual physical churning and movement of the atmosphere itself. By tracking the chemical reactions right alongside the physical movement of the gases, clouds, and droplets all at the very same time, they were able to create the most detailed, realistic simulation of Jupiter's atmosphere we have ever had.
And wow, did this flip the script on what we thought we knew? We used to just assume that atmospheric diffusion, which is basically molecules moving vertically up and down through Jupiter's layers, happened pretty fast, like in a matter of hours. But this new model proves that this vertical movement is actually 35 to 40 times slower. We are talking about a single molecule taking several weeks just to drift through a layer. That completely changes our understanding of its internal weather. revealing an atmosphere that circulates way more slowly and mysteriously than anyone guessed. But here is the absolute biggest plot twist from that University of Chicago study. The model revealed that Jupiter actually contains roughly 1.5 times more oxygen than the Sun. This is a massive revelation. For a long time, there's been this really heated debate in planetary science about Jupiter's oxygen levels. Some older estimates even suggested it had only a third as much oxygen as the Sun. So finally pinning down this supersolar abundance of oxygen is a massive clue about how the planet actually formed.
So why is oxygen such a game changer? Well, way out in the freezing cold reaches of the outer solar system, oxygen is mostly locked up in water ice. If Jupiter has this huge concentration of oxygen, it means it must have accreted a massive amount of water ice when it was forming. And that strongly suggests Jupiter didn't just quietly form exactly where it sits today. To sweep up that much ice, it likely had to migrate, physically moving through entirely different regions of the early solar system.
This massive accumulation of ice ties in perfectly with our modern understanding of planetary migration, specifically something called the NICE model. This framework proposes that our giant planets, Jupiter, Saturn, Uranus, and Neptune, did not just stay put where they were born. Instead, they violently reorganized themselves, migrating and crashing through the primordial Kuiper belt long after the original gas disk of the solar nebula had totally faded away.
So, picture this chaotic era unfolding in distinct phases. At first, the planets were on these neat, well-behaved circular orbits kept in a stable resonance by the gas of the solar nebula. But the moment that gas dissipated, the whole system became completely unstable. The planets broke their resonant locks, and that triggered a period of extreme migration and instability. The outer planets got pushed outward, violently crashing into the primordial Kuiper belt and scattering ice and rock absolutely everywhere as orbital energy shifted around.
And right in the middle of all this incredible instability, we get what astronomers call the jumping Jupiter scenario. While the other giant planets were being pushed outward, Jupiter basically bullied its way in. Through these really intense gravitational interactions, possibly even tangling with a Neptune-sized ice giant, Jupiter migrated radially in toward the Sun. But it didn't just slide smoothly, it moved in numerous tiny, sudden jumps, literally scattering other massive bodies out of the way as it bullied its path inward.
The aftermath of that violent migration is just staggering. Jupiter's chaotic journey completely destabilized the outer solar system and absolutely shredded the primordial Kuiper belt. But crucially, as it jumped around, all that gravitational chaos allowed Jupiter to capture massive swarms of asteroids, the famous Trojans, locking them into stable gravitational pockets right ahead of and behind it, known as Lagrange points. It even played a huge role in sculpting the modern main asteroid belt that we see today. It really was the great architect of the chaos.
When you piece all of this incredible history together, the words of Ji-Hin Yang, the lead author of that University of Chicago study, really hit the nail on the head. We are talking about the biggest object in our sky besides the Sun itself. And we are just now realizing that its atmosphere moves dozens of times slower than we thought, that it is hiding vast amounts of oxygen, and that it literally bullied its way through the early solar system. Planetary formation is just uniquely, beautifully complex.
Which leaves us with a pretty thrilling question to ponder. As NASA's Juno spacecraft continues its incredibly daring, looping orbits, literally diving between intense radiation belts and skimming just thousands of miles above the cloud tops, we have to wonder. We've figured out the liquid metallic hydrogen, the dissolved fuzzy core, the supersolar oxygen, and that violent jumping Jupiter migration. But down in those dark, crushing, electrically charged depths, what other cosmic secrets are just waiting to be uncovered? For sure, keep your eyes on the King of Planets, because this story is far from over.